I could have come to New York, but just didn't work today. But hopefully, maybe another year I can come down and give an in-person talk. So, so what I'm going to be talking about today is about descents on certain types of multi-permutations that I'm going to define what they are. This was originally two separate talks, one about non-crossing permutations that had a different name, quasi-Stirling permutations. And then I realized there are some related permutations that I like to call non-nesting, and you'll see why. But the tools that we use in one place and the other are pretty different. Okay, so let me tell you a little bit about the background first. So if you have a sequence of numbers, for example, this sequence here, we say that a descent is a place where the sequence goes down. And I'm not requiring these numbers to be all different. There could be some repetitions. So descent is a place where it goes down, or the last position. I'm going to make this convention, and I call it a descent too. Depending on what books you look at, sometimes it's considered a descent, sometimes it's not. But for my formulas, they will look a little better if I make it a descent. Okay, so similarly, we define an ascent, which is a position where the sequence goes up, or also we have this convention that the beginning is an ascent. A plateau will be a place where the sequence repeats the same value. And then I have these statistics that keep track of the number of descents. This should say ascents, and then the number of plateau. So descents, ascents, and plateau. Okay, so here's an example. I have this sequence. If you want to count descents, you can look at all the places where it goes down and the end also. And then there are 1, 2, 3, 4, 5 places. Then these are the places where it goes up, and these are the places where it stays the same. Okay, so these are the statistics I'll be interested in. So let me tell you a little bit about the classical what's known about descents on permutations, which is something studied for many years. So I'm going to use this notation, the set of permutations of the numbers from 1 through n. I'm going to denote it Sn. And then there are these polynomials called the Eulerian polynomials, which just keep track of how many permutations have each number of descents. So one way to think about it is you add over all permutations a variable t to the number of descents of that permutation. So for example, if you look at permutations of size 3, there are 6 of them. And for each one of them, you could count descents. So this is the only one that has one descent, with my convention that the end is always a descent. So that contributes this term t. Then there are 4 permutations that have 2 descents, and these contribute 4t squared. And then there is one that has 3 descents, and that contributes the t cubed. One thing that we notice with these polynomials is that they are palindromic. So if you read the coefficients from left to right, it's the same as you read them from right to left. The reason for that is that if you take a permutation and you reverse it, the descents are going to become non-descents. So that gives you that symmetry. Okay, so these are called Eulerian polynomials. Oh, I see. There's a comment by Tom on the, okay, plateau should mean ascent, plateau, descent. Okay. Okay, well, I used that term from a previous paper, but yeah, maybe I should call it level or flat. But anyway, today it's going to be plateau because that's what I've written on the slides. Okay, so these are called Eulerian polynomials because Euler studied them, but he was actually not looking at descent on permutations. So what he was looking at, so here's the picture of the original paper, and you can see these numerators are the Eulerian polynomials. So he was actually looking at some formal power series, and these were the numerators that appeared. So specifically, he was interested in this series. So if you sum m t to the m, you get this series here. And if you sum m squared, then you get these other series, m cubed and m to the 4th. And if you look at these numerators, they are the Eulerian polynomials from before. And this is how they came up in work of Euler. So more generally, if you take this power series where the coefficient of t to the m is m to the n, then you get a quotient where the denominator is very simple and the numerator is the nth Eulerian polynomial. And the way to prove, one way to prove this, that these permutations come up here, is basically to differentiate this equation. And if you differentiate, you can get a relationship between an and the derivative of an, and then you can relate each one of these to the previous an minus 1 and get some recurrence for the Eulerian polynomials that basically is the same recurrence that you would get here. So it's not too hard to show this. Okay, so so now we have the Eulerian polynomials. You can also consider the generating function. So this is an exponential generating function with another variable z, where the coefficients are the Eulerian polynomials themselves, and that one has a nice expression. This is also well known. This could be deduced easily from the previous page. So we're going to use this generating function later. So I just wanted to mention it here. Okay. So so there's another classical definition that I will use. So there are the Stirling numbers. So the ones I'm going to be interested today are the Stirling numbers of the second kind. So then Stirling numbers of the second kind count partitions of an n-element set into k blocks. So for example, S32 is equal to 3, because if you take the 3-element set 1 to 3, and you want to partition it into 2 blocks, these are the 3 ways that you can do it. Okay, so now Gessel and Stanley, back in 1978, were considering some series that look a lot like the ones I had before, but instead of having powers of m here, now you have these Stirling numbers of the second kind. And they noticed that if you put these Stirling numbers of the second kind where the 2 parameters are shifted by 1, you get this. If they're shifted by 2, you get this. If they're shifted by 3, you get this, and so on. And they noticed that these numerators always seem to be a polynomial with positive integer coefficients. The denominator always is 1 minus t to an odd power. But they were interested in this numerators and to understand why they have positive coefficients. So then to study this, they came up with some multi-set permutations that they called Stirling permutations. So let me tell you what they are. So I'm going to use this notation. Maybe this is not very standard, but I didn't have a better notation for this multi-set. So this is a multi-set that has 2 copies of each number from 1 through n. Okay, so you take this multi-set, and now we're going to consider permutations that avoid the pattern 2, 1, 2. So let me tell you what that means. This is with a modern pattern terminology, but the way they define it in the paper is just by saying that there do not exist 3 indices, so that if you look at the values at those positions, pi I, pi j, and pi k, they are not in the same relative order as 2, 1, 2. So that means that you cannot have that the first is equal to the third, so the first is equal to the third, and then the second is smaller. If you had that, then pi I, pi j, and pi k would form an occurrence of the pattern 2, 1, 2. So we don't want that. Okay, so and I denoted by q sub n the set of Stirling permutations of this multiset. And just as an example, this permutation here, you can check that there is no occurrence of 2, 1, 2. And however, this one has these red numbers, the 3, the 1, and the 3, form an occurrence of the pattern that we don't want. So this is not a Stirling permutation. Okay, these are all the Stirling permutations with n equals 2. Now, if you want to count Stirling permutations, that's actually pretty easy, because once you realize that the 2 occurrences of n have to be next to each other, because if they weren't, there would be something in between that would be smaller than n. So then n together with that and together with the other n would form a 2, 1, 2, and we don't want that. So the n have to be together, and in fact, you can insert an n anywhere in a Stirling permutation of size n-1, and that will give you a Stirling permutation of size n. So this gives you a recurrence to count Stirling permutations, and when you multiply it out, it just gives this double factorial. Okay, so these are easy to count, but what's more interesting is when you look at this distribution of descents on these permutations, and this is why Gessel and Stanley were looking at this. So, so I'm going to define these polynomials that I call Stirling polynomials. These are just the same that we did for regular permutations, but now these are Stirling permutations, and you add t to the number of descents. This is how the first few look like. Now they are not longer palindromic, by the way, so but that's okay. And what they prove in that paper, Gessel and Stanley, is that the power series they were looking at, where the coefficients were the Stirling numbers of the second kind, are a quotient of polynomials where the numerator is counting Stirling permutations with respect to the number of descents. Okay, so this would be some sort of analog of the Eulerian polynomials, where when you change the coefficient of the series, these become these polynomials. And I guess the denominator also changes a little bit in that this power is now an odd power. Okay, so this is how these Stirling polynomials were studied. Now I'm going to tell you something that's less classical. Well, I guess I'll tell you a little bit about the literature on Stirling permutations first. So there's a lot of papers about Stirling permutations. I'm just going to mention a few that will be relevant to what I say later. So, for example, Bona showed that these Stirling polynomials not only count the Stirling permutations with respect to descents, but also with respect to plateaus. So plateaus and descents have the same distribution. It's also known that this polynomial has only real roots, and that the distribution of the number of descents is asymptotically normal. So that what that means is that if you were to draw a histogram, how many permutations, how many Stirling permutations have 1 descent, 2 descents, 3 descent, and so on, you'll have some histogram, and when n gets very large, that looks like a bell curve in the limit. Then more generally, Janssen showed that if you look at the joint distribution of ascents, descents, and plateau, then that's asymptotically normal too. This is just a fact terminology. Sometimes the coefficients of these Stirling polynomials, sometimes they are called second order Eulerian numbers, because they sort of generalize Eulerian numbers in some way. Okay, so let me tell you about one way to generalize these Stirling permutations. So turns out Stirling permutations are closely related to some labeled trees. So let me tell you what these trees are. So these increasing edge labeled plain rooted trees. So this sounds very long, and I never know in what order I have to put these 4 adjectives. I know there's some rule in English when you have a noun and a bunch of adjectives, they have a particular order, but I looked at the rule and I didn't know how to classify these adjectives. So I'm just ordering it like this, but it may not be the right way. But I'll tell you what each one of these words mean. So so rooted just means that the tree has a root that I'm going to put at the top, distinguished vertex. Plain means that the order in which I put the children of a vertex is relevant. So if I were to switch the order of the children, that would be a different tree. Edge label just means the edges have labels from 1 through n, where n is the number of edges. And increasing means that if I go down from the root to a leaf, the labels I see increase. So for example, if I go down this way, I get 2, 5, 8. So those labels are increasing. Okay, so there is a pretty simple bijection between these trees and Stirling permutations. And this was found by Janssen, and then he realized they had been found previously. And basically what it does, this bijection, is you just read the tree in doing a depth first walk. So you basically start at the node and you go around as if you were a worm like this. So you now see a 4, then you see a 6. Now you go around, you see the 6 again, then you see the 4 again, then you go down this edge, you see a 1 again, then you go around this way, you see a 2, a 7, a 7, a 5, 8, and then you go up 8, 5, and so on. And eventually you get back to the root. And when you do that, the permutation you see is a Stirling permutation. Okay, so there's a question if we can just label the vertices. Yes, there's an equivalent way to do this. If you do it carefully, it will be equivalent. But well, because the number of edges happens to be n, and that's how it seemed a little bit more natural to do it this way. But yeah, you could push each edge to a vertex, and then the root doesn't get labeled. And if you read it carefully, you'd still get the same. Okay, so okay, so this is the bijection, and now here we can okay, so you have 0, but then, well, then the permutation here would have a 0, or maybe you don't. Okay, maybe you don't read that. Oh, yeah, there's a way. Yeah, there's a way to do it properly. Okay, so now the question, first question I'm interested in, and this is actually how I got into this problem, because I went to a talk where they were doing this. So they were considering, so some authors I mentioned in the next slide, they consider what happens if we remove the increasing condition on the tree. So you have all these adjectives, but without the increasing one. So you just have labels from 1 through n, but they don't have to increase. You could still apply the same map, and you would get some permutation where each number appears twice, but then what would that be? So obviously it's not going to be a Stirling permutation anymore, because, well, the fact that these labels were increasing it's really what's making this permutation avoid 2, 1, 2. And if that's no longer true, then what permutations do you get? Okay, so here's an example. This is a tree that's where the labels are no longer increasing. And if you apply the same map, you get this permutation where each number appears twice. And so Archer, who was a former grad student of mine, Cassie Archer, and these are some undergrads at that time that she was working with. So she proved that they proved that there's a bijection between this set of trees without the increasing condition and certain permutations that I'm going to define in the next slide that they called quasi-Stirling permutation. So let me tell you what this set is that you get on the right. So a quasi-Stirling permutation, and you can ignore this word for now, but in a minute it will make sense why I call it non-crossing. They just call it a quasi-Stirling permutation. So it's a permutation of the same multiset as before, where every number appears twice, that avoids these two patterns. So that means that there are no 4 entries where the first is equal to the third and the second is equal to the fourth. And they denoted that by QN bar. So these are the quasi-Stirling, or I like to call them non-crossing permutations. And here's some examples. So this one here, you could check that it's non-crossing. However, this one here, it's not a quasi-Stirling permutation, because the there's a 3, 1, 3, 1 that violates the condition. Now there's a way to visualize this that it makes it much faster to check. So if you have this permutation here, you could draw an arc between the 2 copies of each number, and then the fact that it's quasi-Stirling is equivalent to the fact that this matching that you get is non-crossing. So there are no 2 arcs that cross each other. And that's why I like to call these non-crossing permutations. However, this permutation here, if I draw the arcs, I have some crossings. So that's not a quasi-Stirling permutation. Okay, so this also gives you a nice way to count them, because you could just think of, well, the number of non-crossing matchings is a Catalan number. And to get a quasi-Stirling permutation, all you have to do is put the label. So basically each arc would get a label from 1 through n, and that would give you the quasi-Stirling permutation. So the number of quasi-Stirling permutations is just n factorial times a Catalan number, which is just the quotient of these factorials. So these are easy to count again, but now if we want to look at the distribution of descent, it becomes more interesting. And in fact, in this talk, I went to where they define these permutations. One question, they had a conjecture about counting quasi-Stirling permutations with the most descents. And this is actually not obvious to see that the most descents you can have in a quasi-Stirling permutation of size n is exactly n. So if you get bored, you can try to show this directly, but it's not. It would seem it's easy, but it's not. It's not like a. I don't think it's a one-line proof. Okay, so this is the conjecture I heard in their talk, and then I was able to prove, which is that if you want to count how many quasi-Stirling permutations have exactly n descents, it gives this beautiful formula, this n plus 1 to the n minus 1, which counts a lot of other famous things like Cayley trees and parking functions. So let me give you a sketch of how we can prove this. Okay, so the idea is to use the same bijection that I described before between labeled trees and quasi-Stirling permutations. So remember, these are the labeled trees with no increasing condition anymore on the labels. So if you consider that bijection, you can look at what the descent of the permutation translates to on the tree, and it's not so easy to describe, but at the end it boils down to looking at each vertex and going around the edges that are incident to that vertex in a circular order and consider some sort of circular descents, and you add them all up for each vertex, and basically that becomes the descent statistic on the permutation. And then with that description, one can study which are the trees where this statistic is maximized. And then it's not hard to see that for it to be maximized, you don't get to choose in what order you put the descendants of any vertex. And therefore, those are in bijection with Cayley trees. And I guess there's one step where you push the labels from the edges to the vertices, kind of like what Alan was saying. So, and so that gives a bijection between quasi-Stirling permutations with n descent and Cayley trees. Oh, Cayley trees is just the what they are labeled. So vertex labeled trees where so these are trees where each vertex gets a label from 1 through n, and there's no condition about plain or not. So you just consider the tree, what's incident to what. So these are the ones that you count using Cayley's formula with the proof for code bijection, for example. Labeled trees, I guess, yeah, okay, labeled trees, okay, these are the same. Okay, so so now we have this formula, but now suppose that we are interested not just in how many permutations have n descents, but maybe we want to look at the whole distribution of descents, like Gessel and Stanley had done for Stirling permutations. We like to do something similar for these quasi-Stirling permutations. So it turns out there is a way to do that, but it doesn't give such a nice formula anymore, but I'll still give you an expression for it. So, okay, so here's what we want to do. So we define these quasi-Stirling polynomials that will give us the distribution of descents on quasi-Stirling permutations. And we would want some sort of expression for these. So the expression that I'll give you is for their exponential generating function. Okay, these are just some examples of the first few, but so I consider their exponential generating function. So here the coefficients are these quasi-Stirling polynomials. So I have this exponential generating function, and just for analogy, remember when we did this for Eulerian polynomials, when you put Eulerian polynomials as coefficients, the exponential generating function had this nice form. Now here, I'm not going to have a nice form anymore. However, I'll be able to give you an implicit equation that relates this generating function that we want to find with this generating function that is well known. So the theorem is the following. So this is the theorem. So if you the exponential generating function for quasi-Stirling or non-crossing permutations by the number of descents has this implicit equation that so it's related to itself via the exponential generating function for the Eulerian polynomials. Or if you don't want to have the Eulerian polynomials, you can just expand, you can just write it like this. So this is an implicit equation for this Q bar. Now, it's not like we can just solve it and for Q bar and get a closed form. However, we can use a Lagrange inversion to get some expression for the coefficients. And if we do that, the coefficients of this, which are the quasi-Stirling polynomials, they are, well, they have this form. So n factorial over n plus 1 times the coefficient of z to the n in this power of the exponential generating function for the Eulerian polynomials. So this gives us some way to compute these quasi-Stirling polynomials. Okay, so it's not like super nice, but it still gives us some way to compute this. And now let me, I guess one could ask, what is the analog of the formulas I had before? So at the beginning, I had this expression for the Eulerian polynomials. They arise as numerators of some power series. Then you could ask the same. So here's what Gessel and Stanley were looking at. So if you put these Stirling numbers of the second kind, here you get the Stirling polynomials that they define. So now, I mean, here we were not looking at the power series. We were rather looking at the polynomials directly, but one could go backwards and say, if you put the polynomials that we have here for the quasi-Stirling case, what would be the series that you get on the left? And well, this is what it is. This can be deduced from the previous theorem. I don't know if this is interesting or not, but it just gives this expression for the coefficients. Okay, so this will be the analog of these other two theorems. Okay, so let me say a few more things about the quasi-Stirling permutations. So there were some properties in the Stirling case. So that the Bona had studied. This is just the classical Stirling case. One of them is that on average, Stirling permutations had 1/3 of the positions were ascents, 1/3 were descents, and 1/3 were plateaus. So it's like a beautiful symmetry you get. In the quasi-Stirling or the non-crossing case, you get a similar theorem, but now it's not 1/3, 1/3, 1/3, but rather you get 3/4 are ascents, 3/4 are descents, and 1/2 are plateaus, roughly. There's some other results that are known about in the Stirling case, or even for permutations. This goes back all the way to Frobenius, that if you look at the Eulerian polynomials, the roots are real, distinct, and non-positive. So the analog of this was proved for Stirling permutations, for Stirling polynomials, sorry. And now we can do something similar for the quasi-Stirling case. So we can also show that the roots are real, distinct, and non-positive. Now, for these two cases, the Eulerian polynomials and the Stirling polynomials, this can be done basically using some recurrence and interlacing the roots. That proof doesn't work here because there's no nice recurrence relating the quasi-Stirling polynomials for n and n minus 1. So it's a little bit trickier, but the final result is still the same. Now, why do we care about the roots, you may ask? Well, if we know that the roots are real, distinct, and non-positive, you can deduce properties about the coefficients of this polynomial. So, for example, one consequence is that the coefficients of these quasi-Stirling polynomials are unimodal. So that means they go up and then they go down, and they are log concave, which means one way to say it is that if you take the ratios of consecutive coefficients of the polynomial, then they are weakly decreasing. Or you could say that the coefficient of in one position square is greater than or equal to the product of the previous and the following coefficient. So that's called log concave. And then another consequence is that the distribution of the number of descents is asymptotically normal. Okay, so all these nice properties that the Stirling polynomials had, they also apply to the quasi-Stirling case. Okay, now there's some generalization where you could consider k copies of each number, and most of the results extend naturally. So in fact, Gessel and Stanley already considered, they define Stirling permutations where you have k copies of each number, and they defined it essentially in the same way. So a k Stirling permutation is a permutation of this multiset where the exponent here just means there are k copies of 1, k copies of 2, and so on, and they avoid the pattern 2, 1, 2. So now we can define, and this has been studied by a bunch of other people too. So we can define the quasi-Stirling version of this just by saying a k quasi-Stirling permutation is a permutation of this multiset with k copies of each number that avoids these two crossing patterns. And if we define it this way, okay, this is just to reconcile the notation with what we had before. When k equals 1, these are just the usual permutations. And when k equals 2, these are the ones I was studying before, the Stirling permutations and the quasi-Stirling permutations. So in general, for arbitrary k, we can also find an implicit formula for the generating function. And I'm not gonna show you what the formula is because it looks pretty ugly, but I'm just gonna tell you a little bit about how we generalize the constructions. So the bijection phi that I had before between quasi-Stirling permutations and edge labeled plain rooted trees. Here it generalizes to a bijection between the k quasi-Stirling permutations and some other trees that I won't define, but I'll give you an example here. So for k equals 3, this is a 3 quasi-Stirling permutation. The kind of tree that we get, it has some these compartments below each vertex. So for example, for this vertex here, this line, this half edge going down is just indicating that whatever is to the left and whatever is to the right is important. So if I were to move this child to the left of this compartment, that would give another tree. So I call these compartmented trees. So every vertex other than the root, I have these two compartments where the children could be on the left or on the right, and where I put them is important. Plus the order in which they are is also important, just like before. So and in general, if this was a k, there would be more compartments, and this is how the bijection works and what we use to extend the results. We can also keep track of the number of plateaus, but I'm not going to write the formula either. So we can do ascents, descents, and plateaus at the same time and get some implicit equation for the generating function. Okay, so this was the part about the non-crossing case. Now I'm going to tell you about non-nesting permutations. And now, if you think of the quasi-Stirling permutations with the non-crossing definition, there's a very natural way to define non-nesting permutations. So the non-nesting permutation, and also you can ignore this other name, canon. I'll tell you later why I like that name too, but let's just call them non-nesting permutations. So it's a permutation of the multiset from before that has 2 copies of each number. And I want a multiset, a permutation that avoids these 2 patterns, which now, so remember before for the non-crossing case, I had 1, 2, 1, 2, and 2, 1, 2, 1. Which were sort of crossings. Now I have these, which are sort of nestings. And if you draw them, it will make more sense. But let's first write it in terms of the values. So that means that you cannot have a subsequence of length 4, where the first element is equal to the 4th and the second is equal to the 3rd. And I'm going to denote by Cn the set of non-nesting permutations. So here's some examples. So this one, you could check it's non-nesting. This one, it's not non-nesting. And the quick way to see it, just like before, is to draw the matchings. So if I have this permutation, I put an arc between any two numbers that are the same. And then here I have no nestings, where a nesting would be an arc that's completely inside another one. So Michelle has a question. So you divide the set of edge labels coming out of each vertex. Oh, for the compartments from before. Yes, exactly. So for higher K, I would have K minus 1 compartments for the children of each vertex, other than the root. Turns out the root doesn't have compartments, but all the others do. Yes, that would be the right definition for arbitrary K. Yeah, so in this, so here for the non-nesting permutations, if I have this other permutation here and I draw the matching, you can see that the arc corresponding to 1 it's entirely above the one corresponding to the 2. So those are nesting arcs, and I don't want that. Okay, so non-nesting matchings are well known, and they have been studied, and in fact they are counted by Catalan numbers as well, just like non-crossing matchings. So this implies that the number of non-nesting permutations is again a Catalan number to choose the matching, and then factorial ways to choose the labels. So you get the same numbers as before. So the number of non-nesting permutations is the same as the number of non-crossing permutations. However, if we want to study the distribution of descents, it's going to be very different. So it's not true that they have the same distribution as before. Now, let me tell you why I also like to call them canon permutations. So an equivalent way to define a non-nesting permutation is that if you look at the first copy of each number, so here it's marked in blue, that will give you a permutation of where each number appears once, like 3, 5, 2, 1, 4. And then you look at the second copy of each number, which is red here. Those two sequences are the same permutation. So this characterizes non-nesting permutation. So a permutation is non-nesting if when you look at the sequence of first copies, that's the same as the sequence of second copies. So that will be useful, and this permutation, I call it S of pi, the one obtained by taking the first copy of each number. Now, this observation is useful when we generalize to K copies, because there are many ways to define non-nesting permutations when you have K copies. And this definition will be the one that I consider the correct one for the purposes of what I'm trying to count here in terms of descents. But anyway, I'll mention that later. But this is why I call them canon permutations too, because if this is like a, like a musical form where one voice sings a melody and then another voice sings the same melody, but later. So this would be like these two permutations where one starts after the other, kind of. Oh yeah, so the spacings are different. Yes, that's true. It will only be the same melody, but different spacings of the notes. Okay. Okay, so our goal now will be to count these non-nesting permutations with respect to the number of descents. And I'm also going to throw in the number of plateaus, just because it doesn't really make it much harder. So I'm just going to put an extra variable there for the number of plateaus as well. So I want to count these polynomials. Oh, I see. Here's the grammar correction. Canon is a noun, so it should be okay. I mean, I'm not at that level. It took me a while to learn that canon with one N is different from canon with two N's, even though it's pronounced the same, or at least to me it sounds the same. Anyway, so, but yeah, that's adjective versus noun. I didn't get that far. Okay, so these polynomials are the ones I'll be interested in finding a formula for them. And just as the comment I said before, that even if you just look at descents alone, it's not the same distribution for non-nesting as it was for non-crossing. And this is very easy to see. For n equals 3 or something, they already look different. So they're not the same. Now, to give you the formula, let me say a little bit about Narayana numbers. So, okay, so a dig path, you've probably all seen this somewhere. So, a dig path is a path. Well, there are different orientations, different ways to draw it, but for me, there will be a path with steps east and north, unit steps east and north, starting at the origin staying weakly below the diagonal and ending on the diagonal. So here's the dig path. And then I'm going to define some statistics on dig paths. So one is the number of peaks. So a peak is just an occurrence of a east followed by a north. Now I realize that if I had drawn them in a different orientation, the word peak would make more sense because it'd be like a peak of a mountain. But in this orientation, it's more like an elbow or a left turn or something. But anyway, I'm still going to call it a peak. Then a low peak would be a peak that touches the diagonal, and a high peak would be a peak that's not a low peak. Okay, so given a dig path, I'm going to denote like this the number of low peaks, by this the number of high peaks. And if I consider the polynomial that keeps track of the number of high peaks and low peaks over all dig paths of semi-length n, this is a well-known polynomial. And okay, if you don't differentiate between high and low and you just count all the peaks, which would be equivalent to setting the two variables to be the same, the coefficients of that are called the Narayana numbers. So this count Narayana dig paths with k peaks. But even if you put t and u, the formula for this is well known. So this is one way to write it. You can write this generating function where these polynomials are the coefficients, and it's this nice algebraic generating function. If you plug in, well, I guess t and u equals to 1, you'll just get the Catalan generating function because the dig paths are counted by Catalan numbers. So I'm going to call this Narayana polynomials from now on. Okay, so these are well known, and the reason I'm mentioning it is because now I'm going to relate the polynomials that I'm trying to find. So these are, remember, these are the polynomials that count non-nesting permutations with respect to descents and plateaus. These are the well-known Eulerian polynomials, and these are the well-known Narayana polynomials. Okay, so the theorem says that the polynomials I want to find are actually just the product of these two polynomials. So the distribution of descents and plateaus in non-nesting permutations is simply an Eulerian polynomial times a Narayana polynomial. And if you set all the variables equal to 1, this makes sense because this is what we were saying before. There will be n factorial permutations here, and there will be Catalan number dig path. So n factorial times Catalan number is the number of non-nesting permutations. But turns out if you just refine it in sort of the most obvious way, it will give the refinement that we want. Okay, so this theorem, like, so I have a proof of it, but it's not like the nicest proof, and I wish there was a nice proof, and maybe there is, I just haven't found it. So I'm not going to tell you much about the proof, but I'm going to tell you about a couple of consequences. Well, here's just an example. If you take, well, the polynomial for all non-nesting permutations of size 3, turns out it looks like this, and you can factor it as an Eulerian polynomial times a Narayana polynomial. Okay, so one consequence, here's one consequence. So let's set u equal to t, and let's just count. Well, I guess if you set u equal to t in the generating function c, that's saying you're just counting descents and plateaus together. So we could call those maybe weak descents. They are positions that are greater than or equal to the next one. So Eulerian polynomials are known to be palindromic. I mean, that's obvious. Narayana polynomials are also palindromic. This is a little bit less obvious, but it's still true. The number of dig paths with k peaks is the same as the number of dig paths with n minus k or n minus 1 minus k. There's a way to do this, so it's symmetric. Now there's a bijection for that, but it's not like so obvious as just reversing something. There's one of the bijections is called the Lalanne-Crevera involution. But anyway, it's known to be palindromic. This is known to be palindromic. So as a consequence, the product is palindromic. So, and you can see this example for n equals 3, these coefficients are palindromic. So that's telling me that because we can interpret this as this polynomial as counting permutations according to so non-nesting permutations according to weak descents, which is the number of descents plus the number of plateaus. The fact that this polynomial is palindromic is just saying that the distribution of the weak descents, the number of weak descents on non-nesting permutations is symmetric. So if you look at the number of non-nesting permutations with R weak descents is the same as the number of non-nesting permutations with 2n plus 2 minus R. And it seems that there should be an easy bijective proof of this, right? Like you have a non-nesting permutation with certain number of descents, you read it backwards, you switch something here and there, and it gives you a permutation with this number of weak descents. Well, I have a bijection, but it's a very complicated bijection that you don't want to see. And basically it turns it to the, anyway, it's way too long. There has to be a simple bijection, but I just haven't found it. So if you have an easy way to prove this with a simple bijection, I'd love to see it. Okay, so this is for weak descent. You can do something similar if you consider descent. So now if I set u equals 1, this Narayana polynomial, now this is now counting big paths with respect to the number of high peaks. And it's also known that that polynomial is palindromic. So, and because this is palindromic, and the Eulerian polynomial is palindromic, so is their product. And here you can see an example. This polynomial, when u equals 1, is palindromic, and what this translates to is to the fact that the distribution of descents in non-nesting permutations is symmetric. So the number of non-nesting permutations with R descents is the same as the number of non-nesting permutations with 2n minus R descents. And again, I have a horrible proof of this that I guess you could consider bijective because it's all a bunch of composing bijections, but it's really ugly, and I'm still hoping there's a simple bijection to show this. Okay, so I'm just going to say a couple more things. You can refine the theorem that I wrote about the non-nesting permutations. You could refine by the permutation of the first entry. So S of pi, remember, is the permutation that you get by looking at the first copy of each number. So if I define Cn sigma to be the permutations, the non-nesting permutations with a fixed permutation of the copies of the first, like a fixed permutation that you get when taking the first copy of each number, then you can define the polynomial just restricted to permutations where this sigma is fixed. And if you do that, you're just going to get the Narayana polynomials multiplied by t to the number of descents. So this is a refinement in the sense that if you add this for all permutations in Sn, you're just going to get the theorem from before. So this gives you some hint to how we would want to prove it, but it's still complicated, the proof of this. I mean, the way that my proof goes, it's basically we interpret the non-nesting permutation here. This is non-nesting permutation. You can interpret it as a Dick path where the rows and the columns are labeled with the same permutation, which is S of pi. So it's the first entries and the second entries form the same permutation. And when you follow the path, if you look at the rows and columns that you're crossing and they're labeled, that gives you the permutation, the non-nesting permutation. So this is just a way to visualize the non-nesting permutation as a path. And now what I guess what I do in the proof is I translate a descent in the permutation, what it corresponds to in the path. Now that's easy in some cases. For example, if this permutation S of pi is the identity permutation, okay, so I should say, if you look at the plateaus are actually very easy to follow, and there's no, I guess this is a bad example because there's no plateau, but if there was a plateau in the permutation, that would be a hill, like a low peak, sorry, a low peak in the path. But if we want to know what descents correspond to in the path, those are hard in general. They're easy in the special case when the the permutation S of pi, when it's the identity permutation, so here I changed the example, so now it's the identity permutation. When this is the identity, then the descents of pi correspond to high peaks of the path. And that's consistent with the theorem, because high peaks are counted by the Narayana polynomial. So the T counts high peaks, the U counts low peaks. So this counts descents and plateaus on the non-nesting permutation, with a specific condition that S of pi is the identity permutation. So these are the ones that are obtained by like shuffling an identity permutation with an identity permutation. So those ones are easy. But if this S of pi is an arbitrary permutation, then the descents correspond to some very weird statistic on the path that it's different for each sigma. So basically for each sigma, for each permutation in Sn, I get a different dig path statistic that has a Narayana distribution. So there are like n factorial different statistics, and all of them have a Narayana distribution. And to prove that, I just have to relate each one to another one, but it's a big pain. So I'm still hoping there must be an easy proof of this simple looking theorem, but I don't know what it is. Okay, so this is the last slide. So we can generalize if you consider k copies of each number instead of 2 copies. But now, as I said, there is more than one way to define non-nesting permutations in this case. So one way would be to say that a permutation with k copies of each number is non-nesting if it avoids 1, 2, 1, 2, and 2, 1, 2, 1. But if you do that, you get very few. When the case is large, you get very few of those. And I mean, you can study the descents, but it's not very interesting. So I think the correct way of generalizing the concept of non-nesting permutation is with a canon interpretation. So now you have a canon with 3 voices, for example, and then each voice has to sing the same melody, even if the spacing is different. And if you define it in this way, turns out, well, here, this is equivalent to considering non-nesting matchings, 3 non-nesting matchings with a definition that there's a paper by Chen, Stanley, and others that considers that definition. So this would be the equivalent to that. And this seems to be the correct way to generalize. And in this case, we can give we can describe the distribution of descents and plateaus, but instead of those Narayana polynomials for dig paths, you get some statistics on standard Young tableau of rectangular shape. They play the role of dig paths. So when you have two columns and n rows, those correspond to dig paths, but in general, you'll have k columns and n rows. Okay, so that's all I have to say. So thank you.
Thank you so much, Lasfrentes speaker.
And I don't know, I still don't hear. Let me maybe while you think about questions, let me see if I can fix the microphone. And if not, we may have to do them on the chat.